All right, hey, let's go over the free response questions now. Let's look at question 11, 11A here. It says a simple pendulum of length, and we'll show a little picture, of unknown mass has the same period as a mass connected to a spring with a spring constant of 125 newtons per meter. Part 1, what is the value of the mass? So these two swing back and forth the same. Maybe I'll consider that one stretched out and this one swinging back, so they'll go like this. All right, so as they are going back and forth, oh, and maybe I need some paper here. Let's look up the concept of the oscillation from the pendulum. And I guess that was in section 4 of chapter 16, and we had this. The period of a pendulum is 2 pi times the square root of its length divided by g. And so a big thing to notice here is it has nothing to do with the mass. And so when they say the simple pendulum of unknown mass, it's kind of irrelevant. It's just, okay, so what? This is the period. It has to do with the length. And in fact, we could actually calculate this number if we want. But looking ahead, it doesn't seem like we actually have to do that, because then it says has the same period as a spring. So if we go back one section to 16.3, we have this, 2 pi over the square root of m over k. And like I said, we could have actually punched those numbers in, and from that, figure out what is the mass. And so the mass affects the period for the spring, but not for the pendulum. But I find it easier just to cancel off the 2 pi, and then you have square roots, and so then we square everything, which just means then that L over G is the same as M over K. And so I guess that would mean that we're trying to find mass. So K times L over G is equal to M. All right, so grabbing the calculator here, we would have K, which is 125, times the L, 0.67, divided by G, 9.8. And we're looking at a mass of about 8.5, I guess I'll round it up, 5 kilograms. Seems like an awful lot of mass. Let me make a note here. Maybe I should check this before we're through. Oh, I know. Well, let's just check this now. This period would be 0.67 divided by 9.8, and the square root of that, okay, times 2 times pi, okay, is a period of about 1.64 seconds. And here, 8.55 divided by 125, square root, times a 2 times a pi. Okay. Okay. All right. So 8.55 kilograms. What is the value of the mass? All right. So there's part 1, and maybe the easier part of it. Part 2, then, is going to have us thinking a little bit outside the box here. It says a second identical additional spring is connected to the mass as shown. And so we hook a mass on the other side. What is the period of oscillation when the two springs are connected? Okay, so now we have 2 springs. And going back to, I guess, section 1 of 16 Hooke's law, we, I guess, did this. We had like this wall. We took a spring, we had a mass, and we would pull at a distance, or we'd pull it with a certain force F. it would stretch the spring a distance x, and because of that, we had a spring constant that was F over X. Okay. But what was neat about that is as we stretch this spring, it pushes back this way as we pull this way of equal and opposite amounts. If you go ahead and put another spring on it, you're now compressing that one. But even though you're compressing it, or maybe I should say because you're compressing it, it's pushing the same way as the first one. So the two springs are actually working together, if you will. The effect is that they're pushing in the same direction. And if you had moved the mass the other way, the same thing would be saying that the red one here would be pushing to the right or pulling it to the right, and then this one would get compressed and also would be to the right. So they push in the same direction, and so you might say the net force, you might even say the effective force, is really the force from the first one and the second one. And here's the other neat thing about Hooke's law is we had this equation minus kx, the minus just meant it is the opposite direction of which you stretch it or compress it. And that kind of makes sense, as we just said. If you pull the blue one this way, it pulls back the opposite direction. But the equation was valid whether you stretched it or compressed it. So what I'm getting at is the first one would be an equation minus kx, but the second one would also be a minus kx, which would really be like saying you don't have two springs, but you have an effective K that is equal to twice one spring. And that's the crutch of this problem. And so hopefully you were able to kind of deduce that, or maybe picked it up on some of the other lessons that we were talking about during the lecture. Because my point is, if the period for a spring is 2 pi over the square root of m over k, then I would just go through the same logic and maybe just call it an effective k, where the effective k is the two combined, which is then two spring constants. So if I take this 8.55 and divide it by two spring constants. Now, remember, one spring constant was 125. So if you double it, it's 250. So 250. This should be the new period, which, by the way, is really just doubling a number that is in the denominator and is also under a square root. So it should be this same number divided by the square root of 2. So I'm hoping that this all works out to be 1.16 seconds for the period. And did it ask for period or for frequency? It's shown what is the period. Okay. Now, just for completeness, maybe I should actually punch these numbers in. 8.55 divided by 250. Take the square root of all of that, times a 2 and times a pi. And yep, there it is. 1.16 seconds. Yay! So there's the answer to part 2, and here's the answer to part 1. Okay. Maybe I should have put here 11A. Okay. And so let's go on here to 11B. And I printed it up here. But 11B says a tornado siren transmits 85 watts of sound energy at a frequency of 640. And so kind of looking at this picture, here's the siren. It sends it out equally in all directions. It says, what sound level does a person hear that is standing, 95 meters away. And then I guess the first step in this is to say, well, what is the intensity at this point? And the intensity is power over area. The power was clearly given as 85 watts of power. And as it spreads out in this sphere, I'll just do the bigger sphere here. I guess blue doesn't stand out real good in that picture. Neither does red. I shouldn't have printed it white on black. But the energy then is spread out over the surface of a sphere. Okay, and so the area is 4 pi r squared. The area of this sphere as these waves go out, which of course as they go out, the radius is getting bigger, meaning the area of the same power is spread out, so the intensity goes down the further away you get from it. And you know that from just real life experience, that as you get further and further away from the source, the intensity is less and less. All right, but taking this 85 and dividing it by 4, also dividing it by pi, and in this case, 95 squared. Let me just double check. Is that what I read? Yeah, 95 meters away. We should be having an intensity of about 7.49 times 10 to the minus 4th watts per square meter. Now, we're not quite done because we need to do the intensity level, which we did one like this a moment ago on the multiple choice solutions, where the intensity goes here, and in the denominator is the threshold of hearing. And so this is a reference to the minimal amount that a normal human ear can hear. So if we divide this by 1 times 10 to the negative 12, take the log of that last answer and multiply by 10, we're looking at about 88.7 decibels. So pretty loud, and you're almost 100 meters away, you're 95 meters away. And it is a siren, so it should be loud. Okay, so pretty loud siren here. Yeah, significantly loud, but not overwhelmingly loud. And now we're going to have this part 2, where I think we get a little bit further away. And so the person in part A begins to run away. So, they hear the siren. Uh-oh. Time to run for the cellar, okay? Away from the siren, and the tone is heard by the running person to reduced to this frequency. And so this is what's going to make part 2 a little bit harder. There's a Doppler effect here. You are the observer, and you are running away. And because you are running away, there is this shift in frequency. And the key step in reading this is to realize that information is going to tell you how fast you are running away. And so, again, we did something like this. I better put a circle around this for part 1. But for part 2, we said that there is this observed frequency, which is connected to the real frequency. Then when we have a moving observer, there would be the velocity of the wave plus or minus the velocity of the observer over the velocity of the wave. Now in the multiple choice one, we had that police car and I think it was a truck. They both were moving. But in this case, we don't need the second factor of when the source is moving. We just have the observer moving. So if we put in our numbers here, we're observing 640 from a 650 source. The default speed is like 340, 342, 343, standard speed of sound in the air. And remember, we use a plus sign if they're coming together and the minus sign if they're going away. And so we would hear a decrease, and it does say going away, so we'll put a minus sign there. And then that should tell us the speed of the observer. Let me just do the 640 divided by 650 first. That would be moving this to the other side. Then I'll bring the 343 to the other side. And so we're looking at 337.7 would be 343 minus the speed of the observer. Move the speed to the observer over here to the left, and then we're going to get our 343 minus this last answer, giving us a speed of about 5.28 meters per second, or about 11 to 12 miles per hour. So they're sprinting, they're running fast. They say, hey, get away. It makes sense. It's a siren. Okay. And so I'll put a little circle around it because we're not quite done, but that's an important piece of information. Because the question goes on to say then, what sound level does the person hear after running for 10 seconds? So if we say distance is equal to velocity times time, this velocity times 10 seconds is 52.8 meters. And so now the total distance away is the 95 plus the 52. Oh, well, I guess I don't need a calculator for that. All right, so we are at 147.95. Yeah, 0.8 meters. All right. And now it's really just kind of a repeat of what we got in number one. So also the intensity is, and so we've got our 85 watts, and our area is 4 pi r squared, but r is now this 147 meters away, which, by the way, as a little side note, sometimes it helps to get familiar with numbers, or at least this is what I tell my engineering students, and maybe it's not as important as the life sciences. But if you look at this is not quite 150, and the original distance is not quite 100. What was it, 95? Yeah. So that's like a 50% increase, So in other words, the radius is going to go up to 1.5 times what it was. And when you square it, that's like squaring 15. It's going to be 2.25, okay? Now, granted, that's more than 2, but just as a rough number, I'm looking at this going, okay, this is going to increase the area by roughly a factor of 2, and a little more than that. It's actually 2 and 10% more. But this is going to then reduce this intensity by roughly a factor of 2. And one thing working with either electronics or sound, a nice thing about decibel levels, and this is probably the side note I could say to you guys as you're kind of working in the field, if you're ever dealing with sound, 3 dBs is always a good one to remember, because 3 dBs is a cut in half. And so if something is reduced by a factor of 2, like this one is going to be a little more than that, we're going to say it drops by 3 dBs. And that means 6 dBs would be a drop of 2 times 2, which is 4. And of course, that's, anyways, electronics in particular, you'll have a cable coming in and you'll put it to a cable splitter, so half the energy goes one way and half the energy goes that way. And so we know that there's a 3 dB drop in intensity once we equally split it. Anyways, this was my way of saying that this would probably be a drop of 10% more than 3. So if we drop by 3, we're at 85. If another 10% is another 3. So I'm guessing we're going to get a decibel level here of about 85.4. But I am sidetracked. So let's get back here to the problem. And so here is the 85. We'll divide the 85 by 4. We'll also divide it by pi. And then we'll also divide it by the radius, which is the last number squared. And we're looking at an intensity of 3.10 times 10 to the negative 4. Which, like I said, if you took this intensity and probably divided it by 2.25, you'll get, kind of close. I did round 150 and I round the other one to 100. Maybe I did too much rounding. In either case, we'll finish the problem for our decibel level. So 10 times the log of 3.10 times 10 to the minus 4 over 1 times 10 to the minus 12. Let me get that. Original intensity divided by 1 times 10 to the negative 12. Let's take the log of that and then finally multiplied by 10. And we are looking at 84.9 decibels. And it is a little lower than that factor right there, but very much in the ballpark. And so this would be the new intensity, just a little over a 3 dB drop. Nice. All right, well, there is 11B, and you can see that the part 2 on this one, as well as the part 2 of this one, hopefully give you a little bit of a challenge. Not so much that it has a negative impact on your grade, that you still learn the physics, but a little intellectual piece and challenge that'll stretch your mind a little bit. And so I hope those were good. Because 11C, and particularly part 2, is definitely the hardest one on the exam, in this one here. And so let's do the part 1 first, and then see what the part 2 is. And hopefully there's a little hint here, but it's not much of a hint on a hard problem. But here we have a copper bar, and so kind of looking at this picture here with a rectangular cross section of 2 centimeters by 1 centimeters, a length L, so here's L, of 15 centimeters, conducts heat from the warmer source over here to the colder source. The warmer source is held at a constant 250 degrees Celsius. So, okay, it doesn't matter how much heat keeps coming out of it for whatever reason. Maybe, there's a heater in here. It doesn't cool down. Or maybe there's just so much, whatever material this is, it really just doesn't cool down. Okay. And if the cooler source over here is 1 kilogram water at 100 degrees. Okay, so at least at first, it's 100 degrees. I know it's going to get harder in part 2 where it changes. But it says here, how long will it take to boil away all the water? Assume energy needed to warm the copper rod is negligible. because obviously when you first hook it up, you got to kind of warm up this into the rod, and so the rod's got to warm up. Although you might argue maybe it's already got there, so it's already, warmed that up, and then the water maybe started colder, which we're going to see in part 2, and then it eventually gets to 100. But this has to only to do with boiling the water away. And of course, what's nice about that, and what makes it kind of easy to do in terms of the calculations, because we don't have a variation with our temperature, and so therefore we only need some algebra here, is that boiling water is always at 100 degrees Celsius. And so the water just keeps kind of boiling away, boiling away, boiling away. In other words, all the energy that flows down this rod goes to break the bonds and free up the water molecules. And this temperature difference, being 150, stays that way the whole time. And so putting two things together, the first one is the conductivity rate. We did this in the multiple choice. Let me look here at the book. I thought conduction. Where is conduction? Oh, it looks like section 5 of chapter 14. You'll find this. The heat per time is the material, the cross-sectional area of that material, the temperature difference, and let me just then call the warmer one over here number 2, and then the cooler one number 1. So the flow of energy here is that temperature difference divided by, your book calls it a D. The diagram I have, which I thought was the same diagram from your book. Oh, maybe this is from the university book. Yeah, because the college physics book uses a D instead of an L there. So, but since my diagram has an L, I'm going to put an L there. Okay. So what I'm getting at least for part 1 here, is that the rate of which energy is flowing can easily be calculated here. We'll start with saying, well, what kind of material do we have? And it said it was a copper bar. And so that's one of the reasons I wanted to look up the book here. I don't know this off the top of my head. Looks like copper has a conduction rate of 390. And I guess I want to be a little careful with my units. Joules per second meter degree Celsius. Now the area is 2 centimeters by 1 centimeter. And so let me change it to meters and then put in an area of square meters. The temperature difference is 150 degrees Celsius. And so that's why I said number 1 is going to be kind of nice, because this temperature difference doesn't change. It's always 150 as this is boiling away. And the length of the rod is a constant number. What did they say in here? Length of rod, 15 centimeters. So let me change it to 0.15 meters. And then hopefully Celsius and the 2 meters cancel left, and we're left with a rate, joules per second, or watt, how much energy is flowing down. All right, so 390 times 0.02 times 0.01 times 150 divided by 0.15. And so we have a rate of 78 joules per second are flowing down. So that's the first part of this. The other part, though, is if this is the rate, and so remember this is equal to Q over T, to get the total energy that flows down, it would be 78 joules per second multiplied by how much time, and that's the question, how much time would it take? And so now we need to know how much energy there is. Well, this is where that latent heat of vaporization comes in. And now we got to go to our change of phase sections, which I think was 13. Yeah, here it is, 13.5. That's just when they talk about it. See, they do a number. There it is, latent heat, 14.3. Okay. And so in 14.3, yeah, they talk about, and where's water? Here's water. And so water takes, let's do this in joules. So I'll have my mass in kilograms. What was it? 1 kilogram? Yeah. So 1.0 kilograms. And my latent heat of vaporization is 2,256 kilojoules. So if you don't mind, I'm going to write that as a joule by putting another 1,000 kilojoules per kilogram. Okay. So that the kilograms cancel, and then the joules cancel, and so the time will be in seconds. So this number here looks like 2,256,000 divided by 78 is going to get me to 28,923 seconds. Maybe I will divide that by 60 for minutes, and maybe another 60 for hours, and about 8 hours. So 8.03 hours at this particular rate. Okay, it kind of makes sense. It's only 78 joules. And then it takes a lot of energy to boil away. That was our latent heat of fusion. Okay, so not the quickest way to boil water. But now let's get to the harder one here in part 2, because it says here, if the cooler body, which we call T1, is this 1 kilogram of, change that to an of, water, it starts at 22 degrees Celsius. How long will it take to warm it up to 100 degrees? So in other words, this is kind of the preconditioning of what would happen for number 1. Chronologically, number 2 would happen first, then number 1. But in terms of mathematics and testing, it makes more sense to ask you about the easier one first in part 1. But the total time would really be, you start with a bucket of water and then you hook it up, and the first thing you have to do is warm up the water. And so the water coming out of a faucet usually is around 20. Now, 22 is a little higher, that's room temperature. But usually in our lab, every time I get water and need to measure its temperature, it's like 19 or 20 degrees. But anyways, so we're starting with some water that's about room temperature, 22 degrees. And then you hook it all up. And so there's going to be a time factor of just getting it to 100 degrees. Then there's going to be this 8 hours we just talked about, getting it all to boil away. We'd go ahead and assume that the energy needed to warm the copper ball rod is negligible. So again, we don't have the extremely hard calculation that would be asking way too much for this level. How much energy goes into the warming up the bar. It's the main reason I picked a kind of a small bar and a big amount of water, so that it truly was negligible. And it's, the details of trying to calculate how much energy, because if you were to hook this up, you probably would start with a copper bar that's also at 22 degrees. So you got to hook it up, and then it begins to warm up, and eventually this side is warmed at 250, and then this side still at 22, and then energy flows down, and this side starts to come up, maybe to 23. So this edge is a little higher than 23, and each little step is a little warmer. Anyway, you can see why I was just saying don't worry about the copper bars. Just too small to be significant. This is going to be hard enough. Just getting how much energy brings it up from 22 up to 100. And there's a little hint here that your delta T changes, so we have to use some calculus. So let's talk here, because this could be pretty tough here. And let's get our variables straight. Now, I've been calling this T1, and T1 is fixed at 250. That's nice. Then there's this copper bar where the energy is going to flow down, and it's going to go to this water, which is at T1. And here's where it's going to get hard, because T1 doesn't stay the same. It is at 22 degrees. And as it warms up to 100, it keeps changing its value. And that's what makes it hard, because remember, up here, the rate of flow, so let's call Q dt, this is the rates at which energy is flowing down the rod, would be this K, A, it's going to be this T2 minus T1 over L. But there's where, like I said, gets kind of hard, because this T1 keeps changing. Now, if we can compare it to number one for a second, we might do kind of a rough calculation. Maybe I'll do it as a cautionary red. But since this is going to be a little tricky, I might want a little bit of a window here of knowing what's going on. Maybe my first thoughts might be, well, how much energy would it take to warm this up? So if I went Q equals to MC delta T, and this is a good time to pause, because this delta T is different from this delta T. See, this delta T is the temperature between the two. Well, this says warm body and cold body. Okay, between the hot and cold object. But this right here, this delta T, is really a delta T of time. It's the same object, but different moments in time. So you might say, this is a delta T of space, and this is a delta T of same object, but different time. So different objects, different time. So I'm going to say this, that, okay, what if I just took this 1 kilogram and went for the specific heat of water? Is that the 4.186 joules per kilogram per each degree? I need to double check that. Let's go. Change in temperature. Let's go back here in the book to section 4. Where's the table. Okay, here we go. We got a table. Here, where's our liquids? Here's liquids. Here's water. Yeah. So they got 4,186 joules per kilogram per each degree. Okay. And it's going to go up. Let's see if that was a 2080. So it's going to go up with 78 degrees. And so this is not a very accurate one. I haven't really got to the heart of the problem here, but if I go 1 times, let's see, kilograms cancels, degrees Celsius cancels, 1 times 4,186 times 78. I would get 326,508 joules. Okay. Now, part of the reason I'm doing that is because if I come back here to part 1, remember it took 8 hours roughly to do 2 million. So I might write this as a fraction of this much energy out of 2,256,000 and say, okay, this is about 14%. So 14% of 8 hours is about 1.16 hours. Now, like I said, that this is not the way to do it, because what I just assumed is that the rate up here in number 1 is the same in number 2. And number 2's rate was determined by the temperature difference of 150. And this is always going to be then lower than 100. That means the temperature difference is always going to be lower than 150. That means this rate is always going to be greater than the rate we got up here. And so I should get something less than 1.16 hours. Now, I hope I'm not wasting your time, because that was, not an appropriate way to do it. In fact, the risk of wasting more time, I probably would have been better off to, if you wanted to make a better rough ballpark, take your 390, your 0.02, your 0.01, your 0.15, and put a temperature difference that maybe is halfway between, because half of the time it's going to be going at a greater rate than that, and half of the time lower than that. So let's see, what is halfway? If I add them together and divide by 2, is a temperature of about 61 on average. So 250 minus a 61 is about a 189, is kind of the middle ground. So if you really wanted a kind of a rate that might be a little better, but still wrong, call it lazy calculus, I'm going to get a rate of about 98 joules per second. So if you took how much energy we need, 326,508, and divided it by that rate, we might get 0.92 hours. And again, that's not a fair answer, completely fair answer. But what it does is it gives me insight to what would be the fair answer. So let me switch back to blue here, because really what I've done is I've taken, a rate on average, a small section, a small change, if you will, and in this case, just kind of averaged it, so I only took the change and divided it by 2. But what I really should be doing is saying, okay, well, what would be the change if it went from 22 to 23? Or maybe even smaller. How about 22 to 22.1? Or how about even smaller? How about a 22 to a 22.000000001? And what I'm getting at then is the instantaneous rate, dq dt. There's the calculus. And so I change my algebra to a calculus. My instantaneous rate would then be something like this, where this number, T1, keeps changing. T2 does not, area does not, K does not, L does not. And then, of course, that number changes. So at first, when we get started with the temperature of T1 way down here at 22 degrees, this difference is kind of high and the flow rate is really, really high. But then it goes up to 23, and so this is a little bit lower. And then it goes up to a 24, and then it's a little bit lower, and then it goes up to a 25. And eventually it keeps going up, and eventually it gets to 100. When it gets to 100, as we know, the rate goes down to a 78. So there is a connection here, a mathematical connection between a microscopic amount of energy during a microscopic amount of time and the current temperature. Now, I say that because we also have, and you see it right here, that the temperature depends on how much energy flows in there. So doing the same kind of calculus here, we might say then that this Q would be a microscopic amount of Q that flows into the mass of water, the specific heat of water, and there'll be a microscopic amount of change of temperature of the water. So that's why I should label this number 1. Now, I suppose I should even put a Q number 1, because this is how much Q goes into number 1. But also, whatever flows down the rod goes into number 1. So that could also be considered a Q1. For that matter, it could also be considered a Q2, because it's also the microscopic amount that came out of here and flowed all the way down into there. But here's what I'm getting at here, is I have 2 equations, and I should be able to eliminate one variable. When you have 2 equations and you combine them together, you lose a variable. And let's see, I have a Q in each one, so I can get rid of the Q's. I don't really have a T. I have a DT and a T here. And I think then what I really want are the Q to be gone. Because see, if those are gone, then I would have something involving temperature number 1, which is good, because I know I want it to go from 22 up to 100. And then something involving time. Now, these would all be microscopic amounts, but let's put them together. So here's what this is saying. If right here we replace this dq with mc dt number 1 over dt, and dt number 1 temperature. And then I have my K, my A, my L. And temperature number 2 is a fixed number, so I don't confuse it. I'm just going to put in the 250 right now. And then I'd have T1. I have a mathematical connection that's basically saying this. The rate of change, maybe I'll write it as T1 dt equals, I'm going to move the MC to the other side. But this is saying then the rate at which the temperature number 1 changes per time is then equal to this, which has to do with the temperature difference. And of course, you can see at first, when T1's only 22 degrees, it's changing very quickly with time. And then as this goes up, it becomes less and less. Eventually, it gets to the stopping point of 100. And, it's going to take longer to get to that second half. That's why I was saying in this model here, well, it would be wrong because we would be treating these two halves equally. And the truth is, it'll take less time to warm up from 22 to the middle than it will from the middle to here. But not in a linear way. By putting the middle, we kind of balance those, but not exactly the same. So it'll be interesting, but I think this is probably a pretty close guess. And this is what I'll call somebody who's, shy of calculus, and say, look, I don't really want to do any calculus, so I'll just do the middle ground. And so you turn a calculus problem into an algebra problem. And actually, if you did that much, that would be great. But this is the real nuts and bolts right here. This is hard. And then fortunately, we just have a calculus problem. And you can see then we have our two variables. We have derivatives, so we have to undo derivatives by doing an integral. And then, this is just doing something like this. If we put the temperatures together, and then the time together. The fancy word we like to say when we're solving our calculus is we do a separation of variables. I have the temperature on one side, and I have the time on the other. And a bunch of constants that could be on either side. Doesn't really matter. But the point is that you have the temperature and the change in temperature, and you have the change in time. And so when you integrate, you are going to get rid of the dt's. And now you're going to have something with just t's in it for temperature, capital T's, and something with t's in it for time. And now you can solve for time. All right, so in this case, if we are doing this microscopic addition in our heads, because remember, that's what this integral is. Remember, this is what this little means. This was Newton's way of taking the letter S and elongating it, because the definition of an integral, f of x dx, is the limit as delta x goes to 0 of a summation of f of x delta x. And that's just this infinite sum. And that's what we're doing. We're doing an infinite sum. We would be saying that, and forget the integral sign for a moment, you would just say if you took one very, very, very short moment in time, say 1 picosecond, and multiply by all this, you would get a corresponding change in temperature based on what the current temperature is. And it might be like 22 degrees. And so you'd get a change in temperature during that 1 picosecond. But if you did another picosecond later on, when the temperature was a little higher, maybe 30 or 35 degrees, this denominator would be a little smaller. So this delta T would be, of course, a little bit smaller. So it's the same microscopic amount of time, but a slightly different amount of delta T. And a smaller delta T as T1 gets bigger. And it makes sense because it comes all the way back to the rate of flow is going to go down as T1 goes up. All right, but now let's actually do the problem here. All right, so what we're going to do is we're going to start this process, and we're going to start with T1 at 22 degrees, and we're going to continue on adding up little microscopic changes in temperature until it gets to 100. And on this side, we're going to take little moments of time. So we're going to start at 0 and add picoseconds to picoseconds until we get to, well, we don't know how long. Yeah, exactly. T. There's the unknown we want to find. And this side's actually a very easy integral, because you can pull constant out in front, and then you just get the integral of dt, which is t evaluated from t. And so that's just KALMCT. That's what we're trying to find, that final time. How much time did it take to get from 22 to 100? Now, this one's a little bit harder. This one, we might have to do a u sub and set u equal to 250 minus t1. So that du becomes then a negative dt1. And so this integral, when we replace dt, we get a minus du over u. And then, fortunately, that's not a too hard of integral, but still one that is not the simplest one, but one you probably could look up real quickly. That's just the natural log of u. And then if I put back what u is, which is 250 minus t1, we have it. Oh, I need to put the limits from 22 to 100. Ka over mlct. And now let's put in our numbers here. I guess I would have a negative ln of 250 minus 100 minus a negative ln of 250 minus 22. The K was 390. The L is 0.02, 0.01. The T is what I'd like to solve for. The L was the 0.15. Mass. The mass is the 1 kilogram. And the specific heat, we already looked that up a little bit ago. Yeah, when we did it right here, there's the 4,186 joules per kilogram. Looks like I'm going to need another page to actually put in my numbers here. Actually, maybe I'll just do this. This would be 150, and then this would be 225 and 3, 228. Maybe I better check that. 250 minus 22, 228. All right, so I'm going to take this side, and actually the two negatives, I'll make a positive. I'll do this in reverse order. This is the natural log of 228. And then I'll subtract off the natural log of 150. Okay, so this side of the equation is going to be 0.4187. This side, 390, 0.02, 0.01, divided by 0.15, divided by 1, divided by 4186. Okay, this is 1.424 times 10 to the minus 4t. And let's see what I get when I take this number divided by this last number. We are looking at 3,370 seconds, or divided by 3,600, and 0.936 of an hour. Yay! And as I said, really, really close to kind of averaging the two. So if, anybody not real wanting to go through or needing to go through all the calculus, we can get some good rough numbers by taking averages, but not as good as the calculus itself. And so that'd be a more accurate number. All right. Hope that helped, and I hope I didn't talk too much. All right. Bye.